So without further ado, I would like to introduce our next speaker. Dr. Anthony Singhal is a professor and chair of the Department of Psychology in the Faculty of Science and the Faculty of Arts at the University of Alberta. He's a cognitive neuroscientist with expertise in neuroimaging methods such as functional MRI and EEG. He does interdisciplinary research with psychiatric populations, driving and human performance, as well as basic research into the neural basis of attention, memory, emotion, and visual motor control across the lifespan. A core part of Anthony's research focus is human performance, safety, and an understanding of impairment risk in driving and other safety-sensitive environments. This focus has been highlighted through his collaboration with Empirica, one of our summit sponsors, over the last 6 years, and which will continue for at least another five years through the generous funding from the National Research Council. Anthony and Empirica are at the leading edge of human impairment through leadership, with an overarching collective goal of establishing a first-of-its-kind scientific blueprint to impairment measurement. If you'd like more information about this, certainly encourage you to visit Empirica's booth out in the hallway and get some information. I think you can also play with some of the tools that Empirica has and that perhaps Anthony will be speaking to. He's here to talk to us on emerging technology to assess fitness for duty and impairments. Please join me in welcoming Dr. Anthony Singhal.
Thank you.
Do you have a clicker?
I do.
Okay,
yep.
Perfect.
Thank you. Good afternoon, everyone. Thank you, Jonathan, for that kind introduction. I spoke at the Fitness for Duty Summit 2 years ago. It was an online version. Had a really enjoyable time, and I'm delighted to be here today to speak to you in person and have the opportunity to meet many of you, and I hope to meet more through the afternoon and the evening. So yes, I'm a cognitive neuroscientist, and which means I'm trying to figure out how the human brain works. And we're doing this with non-invasive techniques like brainwave recording and MRIs. And the questions that I'm interested in studying are related to application. We work with patients, psychiatric patients, neurological patients. I'm interested in human performance in particular, interested in driving research. We've done research on the International Space Station looking at impairment associated with zero gravity and what that's going to mean for astronauts over a long haul if we're going to put humans on Mars. And as Jonathan said in his introduction, we've been working with the folks at Empirica and developing new technology that's based in cognitive science and is designed, and you'll see in the data that I'm going to show you, is starting to reveal some of the underpinnings associated with impairment risk and impairment risk as it applies to driving and human performance in the workplace. So before I start, I have to thank my team at the University of Alberta. This is a pre-pandemic photo of my lab, and I also want to thank our generous funders and collaborators. And so when I say we, I of course mean them. So the primary goals of my approach to all of this, so, the big picture is that, I'd like to make a difference. I want to use a scientific approach to creating safer roads and workplaces. I think that's worth my time to do that. And what we're doing now is we're testing and further developing impairment risk assessment tools, and I'm going to talk to you about that through my talk here. And of course, the goal is for this to be applicable to a large range of industries, large range of settings, and of course, different purposes. So I'm going to talk to you today about cognition briefly, cognition in driving briefly, and then walk you through 4 studies that we've done. I'm going to show you some data. I won't go into the weeds of all the analysis techniques, but I'm happy to talk about it later if people are interested in that. And so I'm going to show you how we've addressed this impairment risk question by looking at different populations, looking at different forms of impairment, looking at different commercial settings, and also different ways of applying the technology to address different kinds of questions about fitness for duty and human performance. So cognition. So I don't want to belabor this point. I am a university professor, which means I like to talk about the theoretical side of things. So we all know what cognition is. You know, there's over 100 years of theory and research that's gone into the development of the tests that I'm going to show you. But they're aligned along these core kinds of concepts. So attention, we all know what attention is. We pay attention, but there are different aspects of it. It can be a volitional experience. You're actively paying attention to me now. But there are other ways that we attend and reflect on things and have reflexive attention. If there was a loud noise or a gunshot in the hallway, everyone would turn to look, even though none of you are actually paying attention to what's going on there right now. We talk about perception. In humans, vision is the dominant sense, but of course our perception of our environment relies on the integration of all of our senses. And so we need to think about how vision and audition, how our taste and smell senses, and of course what our task goals are, all integrate. Memory, we know what memory is. We encode information, we store it, we retrieve it. We have short-term memory, long-term memory. I think memory is a very good proxy for overall cognitive health. And I'll show you some examples of that. And decision-making, making judgments. So this is a higher level kind of thing. You have a goal in mind. You have to invoke a strategy, perhaps. You have to use things from other aspects of cognition to invoke some kind of action. And action, this is an interesting thing from a theoretical point of view. We think about cognition is one thing. I'm attending, I'm remembering, I'm perceiving, I'm making a decision, and then I act. Action is something after cognition. The most recent information is that that's not actually what's happening. That cognition is really an important part, action is really an important part of our cognition. And moving is thinking. And part of the reason I'm pacing around is because it's helping me to think. And then we think about the emotional realm. Effort is very important, motivation is very important, and we have to, try to balance the effects of these things on cognition. And then impairment, and I know there are lots of impairment experts in the room. Different forms of impairment. There can be permanent impairment, of course, and temporary impairment. It can be related to substances, can be related to neurological deficits, long-term permanent effects. Stresses can be impairing. Workload and fatigue can be impairing, both actively and passively. And so I'm going to touch on some of these things as I go. And of course, I probably don't have to tell this audience that cognition is a really important aspect of driving. Driving is complex. We have to make lots of decisions. Training is important, etc. And we also know the severe cost of collision and related injuries and deaths. I think the folks at TURF out of Ottawa in 2018 published a document saying it was about $25 million a year in Canada. So this is obviously a very important thing for us to be working on. And as I mentioned, impairment can be permanent and temporary. In terms of assessing driving performance, obviously an on-road assessment is an excellent way to do it. Simulation, training, and testing is also important. Neuropsych testing, medical and physical testing and assessment is important. And office cognitive testing as well. And so the work that we're doing integrates all four of these things with an emphasis, I think, certainly in the way I'm going to deliver it to you today, connecting on-road performance with performance off-road or in a lab or in an office. So the technology that I want to talk about is broken into 4 tasks. And so this is based on, as I said, decades of very well done cognitive research. The textbook standards of research are the underpinnings of these kinds of testing. And so the VITALS cognitive screen, and VITALS is Empirica's name for this cognitive screen, consists of 4 tasks or four parts. So the first thing is a reaction time task, so it's measuring speeded performance. And we know speeded performance is a good proxy for general attentional abilities. And I'm going to say a little bit more because I think it's important for you to understand some of the subtleties of this before you can appreciate the results. There's also a judgment task where the participant or the subject or the patient has to move a cursor through some obstacles with an end goal in mind. So there's a decision-making that has to happen. There's a memory task that has different levels of complexity, and there's a sensory motor control task that's and what I didn't mention, these are all on handheld tablets. For the purpose of this testing, it's done on a desk, but there is an aspect where the patient or the subject can actually move the tablet as if it's a steering wheel to maneuver some virtual stimuli through some obstacles, and that's what we call the control task. So we've got low-level cognition, we've got higher-level decision-making, memory cognition, and we have some perceptual action components to this. So the reaction time task is really simple. So each one of these squares represents the screen of the tablet. And this is all delivered by trained and certified instructors. And so it's really simple. At the low level, there's some lights here, there's two buttons here, and the participant pushes one button, and one of the lights turns on, goes from red to green, and the subject has to push the button again. So it's a very simple reaction time task. And people do this with great ability. Unless there's impairment, as you'll see. The more complex version is actually what we call an attention switching kind of task. So now there's another stimulus here. It's this box that can move to the right or to the left, but the participant has to wait for the light to move to the left or the right. So in some conditions, the box and the light are on the same side. We call those congruent conditions, and on some conditions, they're on opposite sides. We call those incongruent conditions. And a strategy that we can't control that we use to do the more complex version is a below awareness threshold cognitive skill where we have to disengage our attention, move it to the other side, and re-engage it. And so that takes a little bit of time. And of course, people are much slower on the second part than they are on the first part, and accuracy also suffers. And if there is impairment, we'll see an even greater difference between performance between the first one and the second one. This is the judgment task that I mentioned earlier. So here, there's also two levels of difficulty. So the cursor, this thing has to be moved with two buttons, it's essentially like a gas pedal and a brake, have to move through some lines that are descending on the screen. And so there are gaps that you can move through. So you have to make some decisions about timing your movement successfully through the lines. And so this is a one-line scenario. This is the simple condition. And then we can add two lines that are not lined up. They're asynchronous with each trajectory. And so this task becomes much more difficult to maneuver through the first set of lines and then through the second set of lines. And again, when there's impairment, differences between the easier and the harder condition can become apparent. And that's why a system like this, to have different levels of complexity, is really important, because that can give you sort of the fine edge to be able to see unique interactions with different kinds of impairment. Maybe drinking alcohol, there won't be much difference. People will be bad on both of these things in sort of a uniform, with uniform magnitude. But using cannabis, there may be a subtle difference where they're 10 or 20% worse on the more complex task. The memory task, this is a very simple task developed right out of the extensive neuropsych literature. So there's an array, as on the left side, of dots, and then after a break, a geometric shape appears. It's a square in this case, and then it disappears, and then there's a screen where you can't see the dots, and then the dots reappear as shown on the right, and the participant has to now recreate the shape that they had seen. And there are different levels of complexity here associated with how complex the shape can be, A six-sided shape is harder to recall than a four-sided shape, and also by the duration of the gap between seeing the object and having to replicate the object. And we like to look at that task in terms of their accuracy of performance and also how fast they can move. And the third task, this is the one that I called the control task, and so this is where they can move the tablet as if a steering wheel, and what they have to do is move a ball. A ball will be rolling down a track, and what they have to do is maintain the ball within a target, which is the circle in this case. So here's an instance where the ball is outside of the target, and they have to avoid, by moving left or right, they have to avoid obstacles that are appearing, and in some cases, obstacles come out of the blue, and they aren't expected. So they're continually moving obstacles while trying to maintain time on the target as long as they can. And this also progresses in difficulty by things moving more quickly and there being more unexpected obstacles that come down the pike. Okay, so that's the overview. So the first study I want to show you is we published a couple of years ago in Transportation Research. And this is a study where we wanted to look at the effects of the relationship between aging and at-risk for cognitive decline and aging. And so what we did essentially was we recruited a population of elderly adults in Edmonton or in the Edmonton surrounding area in Alberta, and half of them were referred for a functional driving assessment by their healthcare practitioner, and they were considered risky drivers, or drivers who are at risk to fail an on-road driving test. And we also recruited a sample of healthy elderly control participants. So this was a very difficult study to do, to recruit 100 elderly participants who have different differential diagnoses. And it becomes a real empirical challenge to work with a population like this that has such variability. But we were able to separate them into an at-risk group and a not at-risk group. One of the issues we had to deal with procedurally was that the at-risk group is considerably older. So they were an average age of 78, where our control average age was just a little bit less than 66 years. But statistically, we could control for age, and we did that in this study. They also underwent the Montreal Cognitive Assessment. We did a simulator task. I have a driving simulator in my lab. So we created a simulation that mimicked an on-road assessment. And then, of course, they do an on-road assessment as well. And so this is an assessment that has been developed by Empirica over many years. It's about a 45-minute drive with an instructor. There's a scoring, a normalized scoring system that can sum to 100 points. And there's many aspects of regular driving that have to be done on residential roads, main busy roads, highways, left turns, right turns, different kinds of intersections, et cetera. So what our questions were, number one, is the vitals package, those 4 tests that I showed you, is there sensitivity to our 2 groups that can be seen in their cognitive performance? That's the first thing we wanted to look at. And then the second thing is overall performance on vitals across the entire population, whatever that performance is, predictive of how they did on their on-road test. So we're trying to connect what's happening in the lab with what's actually happening in the real world. So here's some data. As I said, we've controlled for age in this study. So the first task, the response speed task, the green lines are the control subjects, and the orange lines are the at-risk group. And so you can see the at-risk group is consistently slower than the control group, which we would expect. So they're slower on all aspects of that response task. When we looked at the 4th task, the bimanual perception task, so we look at how long they spend in the target, that circle, how many of the objects that are fixed they avoid, and how many of the surprise objects they avoid. And again, you can see, now it's flipped, being up is better performance. that the green lines are consistently higher than the orange lines, suggesting that our at-risk group was not performing nearly as well. So not surprising, but also important to elucidate. There it goes. On the judgment task, this is the second task. So again, you can see when we look at how long it took them to maneuver through those lines that are dropping from the top of the screen, the impaired the at-risk group, the impaired risk group, was taking considerably longer than the healthy controls. And you can see on the left side of the panel that they're obviously the healthy group are doing much better in terms of overall success, and of course the impaired group is having many more collisions in that task. So there's a reciprocity, of course. It would be hard to be high in all three of these graphs, but they're different ways of looking at the same question. And then finally, on the memory task, as you might guess, in terms of the number of correct shapes, so this is the accuracy measure here, not surprising that the controls are going to do much better than the targeted group. And you can see a drop-off in performance after about trial 9. Overall performance in both groups drops, and that's because this is measuring the more complex part of the task. But there doesn't look like there's any interaction. There seems to be an overall decline on their accuracy on memory. When we look at how long it took them, of course, now we're going to see the reverse, where we see the at-risk group taking longer to complete the task compared to the control group. And the reason there's this big jump is because on the left side, these are the easier ones that don't take very long to do, and on the right side, they're the more complex ones that take longer. So the other thing that this shows is that we can employ strategies when we do a test like this. We all do this kind of thing every day. If we want to be really accurate, we slow down on something. And if we want to be really fast, we have to basically accept that we're going to make a few more mistakes. That's not what's happening here, because the cognitive impaired group is both doing poorer in terms of accuracy and also slowing. So this is not because they're giving up one in favor of the other. There's actually something more organic happening that's making a shift in how we would interpret this kind of data. Now, the really original part of this, and this is why we got it published quickly in a very good journal, had to do with the prediction part. So we used a machine learning approach, an artificial intelligence approach, to put all of the data from the vitals tasks and look for predictability in terms of a particular score that would actually pass on the on-road or fail. And so these graphs, I won't go into the bones of these. They're called receiver operating characteristics curves, and basically the way to interpret them is that when the curves are further towards the top left corner, the better the prediction. And so the number one predictor, this won't surprise you, the number one predictor in this study for performance in terms of passing or failing was age. Not surprising, because we had a much older group that was also the at-risk group. But of course we can control for that, and when we do that, this represents all the different variables of all of the 4 tasks that showed significant predictability, and when we combine them all, we did a number of different approaches. We found with about 81% predictability, performance on the vitals was showing, was predicting whether they would pass or fail on the test. Now, it's true that fewer people failed than passed, but there are statistical tricks, essentially, that are accepted in my profession that we had to invoke for that. Okay, so the summary of this, all the components of vitals reliably showed differences between our groups. I think you saw that. That's the blue versus orange lines. And with a relatively small sample size, to do a machine learning approach with less than 100 people is really, it was noteworthy. Of course, there was a lot of data because we had hundreds and hundreds of data points for every person, so we had good power from that point of view, but to be able to find better than 80% with less than 100 people was significant. And so our argument in that paper and at this point of the research that this has important implications for medically at-risk drivers and other populations. And if I haven't been explicit about this from the get-go, we are viewing, and I am viewing, in this context, driving as being a proxy for other skilled performance. Okay, the second study now, we're shifting now. So now we're not thinking so much about predictability for driving performance, but we wanted to see if the vitals would show sensitivity to different kinds of impairment in a larger sample. So this was a drug study that is not published but is under review now. I expect to be published in the coming weeks. That was part of my graduate student Michelle Tomczak's recent thesis defense. So this audience knows about cannabis and cocaine. I think in the cognitive realm and human performance realm, there's a lot more known about cannabis than cocaine, and that's true of driving. But when we think about polysubstance abuse, so people who are taking, in this context, cannabis and cocaine, even less is known relative to a cocaine group. And one thing that becomes important in a study like that I'm going to show you is the time course of the drugs. So cannabis has a much slower trajectory of, peaking its effect in the first hour and then taking many hours, to come back to baseline or below baseline, whereas cocaine will spike in 30 minutes and then depending on the neurotransmitter systems can drop well below baseline within that first hour. And so there's a wear-off phase that's likely related to the very high addictive part of cocaine use. And of course, there are different theories about how these drugs operate on the brain, of course, and how driving under the influence of these drugs can be different. And so what we're interested in this study is to compare a large group of almost 400 adults under the influence of substances with almost 300 young adults that were recruited from the University of Alberta. So these are university students who participate in this as part of, for school credit, essentially. And then the 47 older adults from our original study. So these are the healthy older group. So our goal is to look for a cognitive profile of substance use using the vitals tasks and try to differentiate cognitive performance between cannabis use and cocaine, and also people who have taken both cannabis and cocaine. And so in this study was done in, the data was collected in Jacksonville, Florida with the folks at Empirica and with the assistance of law enforcement. So this is part of a drug recognition expert training session, and so for compensation, adults who have taken these drugs will come in and they have a urine screen, a urine analysis, and then as part of what they go through, do the vitals as well, the vitals tasks. So we make an assumption here is that none of these people should be driving. So the questions here are not to look for predictability of whether you should drive, because in our view, all 376 of them were not fit to drive. So this shows you our demographics. So you can see the numbers. It's not perfectly balanced. This is CAN means cannabis, COC is cocaine, and then of course cannabis and cocaine together. Our control older group from the previous study, and then the newly collected younger university student group. And so you can see the ages here. Of course, the university students are the youngest, the oldest are the oldest, and of course there's in the drug group, we're in the middle age range, with the cocaine group being the oldest and the cannabis and cocaine group also being substantially older than the cannabis alone group. So again, we have an age problem that we have to adjust for, which we do. So here are some results, and again, I'll try to summarize these in easy to digest ways. So if we're looking at how fast they're doing stage 1, the first reaction time task, what we see is that and so it's stage 1 and stage 2, that the young adults are the fastest. And after the young adults, it's actually the cannabis group that's the fastest, which is the second oldest group. And then the elderly group in red is next, and then the cannabis and cocaine group are the worst. So age is winning out here, using drugs is losing out, particularly cocaine. When we look at the judgment task, and we're looking at decision making in terms of having collisions with those lines, we see something similar. Of course, the young group is doing the best. In terms of early stage collisions, the elderly group is doing the second best, and the drug groups are doing the worst. And when we get to the more advanced version, it's actually the elderly that are now doing a little bit worse than the cannabis group, with, again, the cocaine and cannabis doing the worst. So again, youth is good, youth is winning out, and cocaine is losing out. And what you may also start to notice as I show this is that when cannabis and cocaine are together, the performance seems to be in the middle of where cannabis is alone and where cocaine is alone. So it may be a sense that in a negative way, the cocaine is anchoring performance in that group when it's combined or when it's cocaine by itself. And the other thing, just as a caveat, which is very important, and so doing a study like this is empirically challenging. So these are important steps to take for us to be able to elucidate new questions that we want to investigate. But because of the different trajectories of the drug consumption, it's very appropriate to assume that the cocaine group are all well on the back end of their experience and are actually in that negative place. And so some of the early euphoric and excitability associated with cocaine is not going to be present in this data. Memory. So how do you think they're going to do on memory? Well, of course, the young people have the most accuracy and are doing it the fastest. The second most accurate group, the elderly adults. The third most, the cannabis group, and of course, the cocaine groups are the worst. And when we look at how long it takes them, again, the young are doing it the fastest, but the cannabis group is second, with the elderly group being more similar to the cocaine groups. And so if we think about this reasonably, this is probably, because it's a speeded thing, and we think about speed accuracy trade-offs, as I mentioned on the previous study, I think this is not really related to more cognitive decline in the elderly group compared to the drug groups necessarily, but maybe related to other physical issues associated with speed, and perhaps even familiarity with tablet technology. And a very similar story comes in the bimanual control task when they're maneuvering down the track, trying to maintain control of the ball while avoiding obstacles. Again, it's the young group that's doing the best, but the cannabis group, which is the second youngest group, is sort of in second place with all of the cocaine group, the two cocaine groups and the elderly having the worst performance. Probably for similar reasons to the previous slide in terms of memory speed. Okay, so the brief summary of this, our tests are showing sensitivity to the different drug groups, particularly when we compare them to our two control groups. So we're seeing age effects, we're seeing drug versus non-drug effects. Certainly the young adults are performing the best. It is the case that the drug use may mimic aging in some aspects of the cognition, but we expect that it's for different reasons. And of course, as I already mentioned, we assume that 100% of this drug group is unfit to drive. So the predictability of performance would be very high in terms of putative on-road performance in my estimation, but of course we don't have the data to back that up. Our third study is one that we've just finished the manuscript, just actually days ago, and are ready to send it out for publication. And so this study, we wanted to look now at the applicability and predictability of the vitals performance with different commercial vehicles, so in different settings. So we wanted to examine performance differences on the vitals as a function of vehicle type. So we wanted to look at light vehicles like cars, vans, light trucks. We wanted to look at heavy vehicles like buses, and we wanted to look at large trucks like transport trailers. And we wanted to examine performance as a function of on-road evaluation performance, of course. So there were unique on-road tests for each vehicle type across different industries, different companies, and with a lot of overlap. So if there were 100 aspects of an assessment between the three driving groups, there was about 4% difference. So there's very good correspondence in terms of how the on-road was evaluated. And of course, we wanted to examine the level of predictability of the vitals for fitness to operate these commercial vehicles across all of our group, our entire industry. I'm doing okay. Okay, so this was a big study. Over 2,000 drivers were recruited here. And as you can see, our three vehicle groups are defined here. Our largest group, not surprisingly, almost 600 of the 2,000 were in the light vehicle category, with the heavy group over 400 being the second largest, and the trucking just under 200. On the right side, at the bottom on the right, what this figure shows is why they were doing the assessment in the first place. And the majority of them were doing it as part of a pre-hire evaluation. So they're motivated to do well on this task because they want to get hired by a company. There was a population that were doing this in terms of a return to work assessment. It's a smaller group, and we were concerned that the return to work group would have a different motivation than the people who are trying to get hired in this case. And so we did two analyses, one with the whole group, and then one where we removed the return to work drivers, and with like one or two very minor differences, the complexion of the data was the same. So this data is framed a little bit differently. So we wanted to look at performance on the cognitive tasks of vitals and compare whether they passed or failed, and compare the three groups, light, heavy, and trucking. And so the yellow boxes are the folks that passed, and the blue boxes are the folks that failed the on-road. And in terms of reaction time speed, you can see that the light vehicles type, when they were faster, they passed more often than when they were slower. So the slower group were failing the on-road. When we look at judgment, again, we see differences in the light group, both for what we call premature starts and overall success. So there's reciprocity in these two figures. So they can be interpreted as one overall effect. But we didn't see any differences in the heavy or the trucking groups. And to cut to the chase on that, our inferences are because those sample sizes are smaller. And so we're seeing differences, so we're seeing some patterns, but they're not statistically emerging because there are fewer people in those groups. And so again, in terms of passing the on-road, the light, better performers on vitals were in that pass group. And this is also true for overall success for the more complex task. We did see a small effect for trucking in terms of proportion of successful trials overall. But when we looked at how cautious they were to beginning the overall task, we didn't see any difference in the trucking group. But again, in the light vehicle group, we saw things. The same kind of pattern of better performance being associated with passing the on-road. And on the memory task, again, you can see that the pattern is similar, particularly between light and trucking. And so in terms of duration, we have significant effects where the faster performers in the light and trucking group were the people that were passing. And when we think about accuracy, the groups that were more accurate were also from the group that was passing. And very similar, of course, for the control task, where time inside the target was associated, more time inside the target, more time on target performance was associated with passing the on-road. Now, when we look at prediction using a machine learning approach, and so here it's an extension of what I showed you in the first study. So here what we've done is classified a score or created a normalized score on the vitals, a composite score that from 0 to 100 associated with likelihood of impairment. And so what you can see when we look at this, so overall there were about 20%, a little bit over 20%, 20.4% I think, of the population failed the on-road. And what you can see is that the likelihood of that failure really starts to spike after a score of about 55 out of 100. So knowing the score from the in-office tests was showing really strong predictability in terms of what on-road outcome would be coming next. So this was exciting for us because this is a much larger sample, and it's a bit more of a robust way to show that predictability between on-road performance and in-office testing compared to our first study. So the vehicle difference effects, I think they're due to unbalanced sample sizes. All of the heavy and trucking group also drive small vehicles, so it seems unlikely that there would be substantial differences, but it was still an open question to ask. And in the literature, the transportation literature, there are questions about cognition and performance associated with these vehicle types. So we can answer an open question from this study. Of course, we saw the pass-fail effects being the largest in the largest sample. That's the small group of almost 1,600. And this is ongoing. We're adding more data. The sample is substantially increased already. So there'll be an emerging story that comes out of this, but overall, the results are just getting stronger. And as I said, the vitals strongly showed likelihood of on-road failure. Okay, so the last project I want to talk about is study 4. And so here, it's a very different kind of approach. So this is a very large-scale study that we did with Transport Canada. So Transport Canada funded project, and we did with the Alberta Motor Transportation Association. And what we were interested in looking at is driver performance, driver experience associated with platooning. So this is where two transport trucks are connected via computer and can be at different distances. And in terms of questions around safety and applicability for platoon trucking in Canada, Transport Canada wanted to know from a human factors point of view, what's the experience of the drivers? And this was essentially a study around active and passive fatigue or workload. And you can imagine that the driver in the first truck is going to be more actively paying attention and working compared to the person in the second truck who's along for the ride. And one of the questions is around passive fatigue, and if that person becomes hypovigilant or actually, just sort of is gapping it because they're bored, because of monotony. So those are the sort of the big picture questions that we're investigating here. And so this was a more substantive study. So we geared the drivers up with portable brainwave recording devices. So we want to look at brain data associated with fatigue. We had dash-mounted eye trackers, so we could look at gaze and blinks and pupil size. We recorded the heart rate variability. We did sleep and fatigue assessments, and we did some cognitive testing, and a major part of the cognitive testing was the vitals. And so here it's different. So this was a live trial that we did. So the trucks would leave from Calgary at the beginning of a shift, pick up a load, drive to Edmonton, drop off their load, and then return to Calgary. And there were different shifts. There was a day and a night shift. And so we did vitals at the beginning of the trial, so when they're in Calgary starting their trip, at the second point when they're in Edmonton, and then at the end of the day when they're back in Calgary. And a lot of other testing too. So the point here, so we're looking at vitals in a different way. So now we're using vitals as a probe task. We're using vitals as a way to look at the effects of the different conditions in platoon trucking associated with overall cognitive performance. So there are lots of different conditions here. I haven't had time to go into those, and it's not going to matter in terms of the story I'm going to show you. And this is this project is still in the works in terms of our analysis, so this is preliminary data that I'm going to show you. But the point is, we're not connecting vitals performance with on-road performance. We're actually looking for different on-road conditions associated with vitals performance. And then we can make an inference about what might be happening in a platooning situation compared to a non-platooning situation, maybe in terms of memory effects or attention effects or some other kind of thing. So I know for all of these projects, the format of the data looks different, but it's the same kind of data. For various reasons, we've used different software to visualize our data. So if I look at the judgment and memory tasks, I'm doing them out of order on purpose. On the left is time point 1 in red, and on the right in blue, the blue rectangles that have data in them are the post-trip data. So we're looking pre-post in this scenario. So if we look at accuracy on the judgment task, really good accuracy, a little bit less when the task gets harder, but no effect of the driving. If we look at time, again, as it gets more difficult, they're slower, but no real major effect in terms of pre or post. There was a small, non-significant, what we would call a statistical trend, where they were actually a little bit faster in the more complex one following the trip. Memory task, it did exactly what we thought it would do. Accuracy is dropping, but speed remained pretty stable in this group. This is a middle-aged, mostly male group of drivers. It's a very small sample. We ended up having fewer than our statistical powering for our brainwave measures mandated, which is another issue for us, and there are lots of reasons which I won't go into here. So again, we're seeing differences between memory performance pre-post, but we're not seeing, easy hard, but not pre-post. And the same on the control task. So as things get more difficult with surprise, obstacles, performance is dropping from easy to hard. But if you remember, I hope, that in the reaction time task, the lowest level cognitive task, which is the first part of vitals, the more complex version had this incongruent, congruent attention thing, where you could simply respond to a light, or you can be cued one way or the other and then respond one way or the other. And they could be both on the same side, you do better, or they could be on opposite sides, you do worse. And so when we look at that subtlety in the data from this experiment, we do see something interesting. So when we look for what we're talking about, the difference between congruent and incongruent, the difference between easy and hard, or not switching and switching. And again, switching in this context is not a conscious thing. This is just one of those things that you can't control. Even if you really tried to control it, you wouldn't be able to do it. It's just so below our awareness threshold. It's just there's a very good reason for us to have this in our behavioral toolbox, but we can't control it. But what we did see is that difference is bigger post-trip compared to pre-trip. So they're doing worse on the harder switching task after driving. So one of the inferences, and it's preliminary, but one of the inferences is that the workload associated with a long day of transport platooning, or not platooning in this case, both scenarios, is associated with more impact on the more difficult aspect of this very low-level cognitive measure. And so the take-home message from this slide and this study in the context of this talk is not about platooning, is about the very fine sensitivity that we're seeing now in this battery of cognitive tests. And so this is going to open the door for us to look at a lot more of the subtleties that are not automatically, but are naturally built in to the design. Okay, so the summary here, vitals was implemented as a probe task for driver workload in this case, and fatigue, as opposed to a direct measure that we would associate with on-road performance. The performance overall was stable. We saw differences between easy and hard tasks, as we would expect, but it's really this attention switching effect that has us a bit excited about what to do next here. And of course, that sensitivity, as I've already said, is below our awareness threshold. Okay, so to summarize, I've shown you 4 studies showing strong relationships between off-road testing with vitals and on-road performance. It's true it's not direct in the second one, but we've looked at it from different approaches. So study 1, we're looking at 2 different populations, an elderly population that is cognitively healthy and one that is at risk to not be cognitively healthy. We looked at it in the context of different drugs and age effects, and we looked at cocaine and cannabis and polysubstance users who have taken both cocaine and cannabis. And we looked at different commercial vehicle types, and with a large sample size, we're able to put that together into a very strong predictive model to show a relationship with cognitive performance and on-road performance. And so the take-home message is that this convergence of findings suggests that this emerging technology has great value, and we're already planning the next set of things that we want to do. This is going to be a multi-year project. We're going to do some more experimentation as part of our emerging work on this, including some more direct brain assessments as well. So with that, I'll stop, and thank you very much for your attention.